Hello and welcome back to my favorite people, and thank you very much for watching this lecture video. In this lecture, I'm going to go through mass spectrometry, and is a technique that we use it to find the molar mass of the unknown sample or the sample that we made it inside the lab, and we want to have a confirmation that we got the sample. The main question that I want to start with is what's the structure of the mass machine and how does it work? In a mass machine, you inject a sample, and that sample very soon it will evaporate, vaporize, and then you can bombard it with a bunch of electrons, and after that one, it will go through fragmentation. And now you have a particle with a positive and negative charge that you can move it in a magnetic field. At the end, you will get a ratio for mass over charge, m over z. M stands for mass and Z stands for charge. You can use this ratio to determine whether you made the sample or not. Okay. So as I said, the first step is going to be injecting the sample. And when you inject the sample, now you bombard it with electrons, electrons that they have high energy. And one technique that we use, we call it electron impact. So I'm going to write it with EI, stand for electron impact, or another technique that's going to be electron spray ionization. And so this is the first technique. That's going to be the second. And the third technique, it will be MALDI technique. And MALDI technique, and both electron spray ionization and MALDI techniques are kind of like a soft technique. They will not create too many fragments. So they're going to be really, really useful when you're dealing with heavy molecules like protein molecules. Okay, so as you see, the first step, it will be bombarding of the sample with a bunch of electrons. What do we get? We get a radical cation. And remember, a radical is going to have one single electron, and a cation it will have a positive charge. So now I got a radical cation. I'm going to show it by here. M, and M, it has a positive charge, so that means it's a cation. And also, I will put this dot to say that's a radical cation. And radical cation is going to have the same mass as the starting compound. The reason for it, because we just ejected one electron from the system, and mass of one electron is 2,000 times smaller than mass of a proton. So I'm going to say mass of proton is way higher than mass of one electron, and mass of proton is almost 2,000 times bigger than mass of electron. That means we don't care really about mass of electron. And whenever we are writing the molar mass, or we calculate the molar mass, we are going after mass of protons plus neutron. Okay, and so that's the reason I say we don't care about it. Now, molar mass or mass of the molecular ion that I showed it by M plus and a dot, that's going to be equal to mass of the compound. And from now, I'm going to keep calling it molecular ion. Okay, so I got a particle that is a radical cation, and that radical cation is not stable. Very soon, it's going to go through fragmentation, or it will technically dissociate. And what will happen? I get a radical that has zero charge. Okay, zero charge. And I get a cation that the charge for it is a +1. Any particle with a positive or negative charge, whenever it starts moving, it will create magnetic field. And so that means you can actually move it inside magnetic field because it has a charge. And so any particle with a negative charge, we cannot really work with, with zero charge, we cannot work with it because it's not going to have a magnetic field. But if it has a plus or minus charge, then that's going to be useful. Okay, what do we get from mass? As I said, we will get a bunch of mass over charges, masses over charges versus their intensity. Okay, and before I'm going to go through this graph, I want to show you the mass machine, and then I will go after this in the graph. Okay, so as you see, we have a place to inject the sample. So I'm going to inject the sample from here. That the sample very soon it will turn to gas because we have a heater, and while it's turning to gas, we can bombard it with electron. Now, when you bombard it with electron, you might get a particle that it has a positive charge. You took one electron from the system. Now you got radical cation, and that radical cation it might go through the fragmentation. It will give you a cation. So I got a species with a positive charge. So let's say we got a species with a positive charge. If I put a negative charge on those plates, I can actually attract, or I can pull that species to the right side. And very soon my particle will move, and because it's in a gas phase, and also there is vacuum, and the speed is going to be really, really high. Now, when the particle starts moving, it's going to have a magnetic field. So we have magnetic field there, and that magnetic field is going to fill the magnetic field of the machine. And so I can use that magnetic field to tune technically or direct the radical cation. And I keep playing with the magnetic field of the machine until I screen all mass over charges that I might get. Now, if you don't tune it, very soon some of them, they might hit the wall here, and if they hit the wall there, they're not going to make it to the detector, so you will not see technically those species. Now let's go back to this this slide. I said the main thing that you get from the mass spectrometry, you get M over Z versus intensity. Okay, and let's jump and go after this graph. And as you see, we have a molecule that is methane, and the molar mass for it is 16 gram per mole. Okay, now when we inject this sample to the machine, it gives us a big peak around 16. So this one is the tallest peak, and from now I'm going to call it the base peak. Okay, so the tallest peak, the one with the highest intensity, let's call it base peak. Next, and the molar mass of our sample is 16, and it happened that the mass or M over Z of the tallest peak or the highest peak is also is 16. So I'm going to say this peak is going to be the radical ion peak or molecular ion peak, that it has mass over Z equal to 16. So in this case, my base peak happened to be technically the molecular ion. And then after it, I see also some peaks that they have lower intensity. And the second peak, it has mass around 15. And the reason for it is just like we lost one hydrogen from the system, and that gave us CH3 or M-1, which is equal to CH3. And it has molar mass equal to 15. Okay, now let's go a bit in deep and talk about this spectrum. And let's try to characterize each of the small peaks that we see around the main peak. Okay, so I said we have a compound that the molar mass for it is equal to 16, and I got base peak that has M over Z equal to 16. So in this case, my base peak is equal to my molecular ion, and these two are equal. And the molar mass for this, or M over Z is equal to 16. Okay, and again, we're going to show this one by M. So M plus dot, that stands for molecular ion. The peak right before it, it has M over Z equal to 15, and the difference between this peak and the base peak is just 1 unit. And the way we show it, we say is the technically molecular ion peak, but it's missing 1 unit. And so I'm going to show it by M-1. Next one, this is missing 2 units, so you can call it M-2. And how about this? Okay, how about that one? You can say M-3. Also, we have 1 peak that is 1 unit higher than 16, and I'm talking about this tiny peak. That's the tiny peak is 1 unit higher than 16, so I'm going to say M plus 1. Okay, now let's go after the reasoning of each of those peak or the sources of them. Okay, why do I see 15, 14, and 13? And we have a compound that is CH4. Molar mass for it is 16. Now, if you lose 1 H, that's going to give you CH3. The molar mass for it is 15. And if you take CH3 and you remove another H, in this case, you get CH2, and that one, it will give you M equal to 14. And CH2, you subtract one H from it, that's going to give you CH, and you will get M equal to 13. Okay, so the top one, when you inject it when you inject the methane to the machine, you will get this. You will get CH4 radical cation. Okay, and we show this one by M plus dot. It has mass equal to 14, we said, or M over Z equal to 14. As 16, my bad. 16. Okay, so we show it by M. Let's keep this one in our mind. We show it by M. Now, the 15, I'm going to say is M, but it's missing 1. And next one, it will be M minus 2. And this one, it will be M minus 3. How about the peak that it is M plus 1? So that means it has a molar mass around, or a mass around 17. And what's the reason for it? The reason for it, okay, we said molar mass. When you calculate the molar mass, you are calculating technically mass of protons plus neutron. Okay, carbon 12, it has 6 protons and 6 neutron. But carbon 13, it has 6 protons and 7 neutron. When you add them, when you add those, you get 13. And the mass is going to be 1 unit higher than carbon 12. So the reason that I see a peak 1 unit higher than 16 is because carbon, like we have a carbon that happened to be isotope. Okay, carbon 13 and 12 are isotopes. We have isotope carbon, and this isotope carbon formed this CH4. This is 13, and we got radical cation. And mass for this one is going to be 17 gram over mole. And as you see, it showed up as a tiny peak on the right side. Okay. Another example. Okay. So the highest peak, regardless of whether it's the last peak or not, we call it the base peak. Okay. The highest peak from now, anytime you see the highest peak, just label it as a base peak. And the base peak and the molecular ion peak, sometime it will be the same. Okay, the last peak that you see happened to be the highest one. And one example is methane. As you see, the last peak that we are talking about it is the highest one. It has the M over Z around 16. Yes, we do see one tiny that you can ignore it. That is just isotope and isotope. So the last one we said is the base peak, and also we called it the molecular ion peak. But they don't need to be the same. And this one is one example. As you see, the base peak is the highest one, and is way less than or way far from the 98. And 98 is our molecular ion peak is technically is a compound or species that has molar mass of the unknown sample or the sample that we injected. And how about the base peak? Base peak is a species that went through fragmentation. And also, I see a tiny peaks close to 98 that we said the reasoning for them is because we are dealing with isotopes. I want you to look to the numbers that we are dealing with. One is 98, and the second one is 83. If you subtract these two, just simply say I have 98, and I'm going to subtract 83 from it. That's going to give me 15. And this 15, you can actually write it as we have a carbon plus 3 hydrogen. Molar mass of CH3 or M over Z of CH3 is going to be equal to 15. So what happened here? If you call this one M, the 83 is the molecular ion peak that lost one methyl group. So I'm going to call this base peak M minus 15. And what's the 15 here is the CH3. I'm going to stop the lecture here, and next lecture I will try to practice more example. And thank you very much.
you.